Hello everyone, my name is Steve Heller. I'm the CTO of Two Misses Corporation, and what I will be discussing today is the title of the lecture or the talk is Challenges and Opportunities in Developing a Hash Table Optimized for Persistent Memory. Now, this title was decided on quite a few months ago. And since that time, of course, we had what we would call the recent unpleasantness from the Intel announcement. And I was thinking, should I rename it the new buggy whip for 2022 because of the persistent memory reference, or should I find something else to talk about in addition to what I had already scheduled that would still be of interest with the new situation regarding persistent memory? So, the new paradigms for new storage technology is still true. You have to write your code differently if you have a very fast storage device. Now the question is, why do we need yet another hash table or key value store? Aren't there enough of those already? I think the answer is there's a lot of them. But this one is a little bit different, and that's what I'm going to describe next. Compare and contrast with existing technology. So here are some hopefully representative algorithms that are that exist already. The three last columns. An unordered map. Everybody who writes in C++ knows what that is. It can handle a variable length. It's not persistent records. It's not persistent. It doesn't. It has performance guarantees of asymptotic nature, but they're not specific to any particular access. It doesn't incrementally rehash. The storage efficiency isn't very good because you have to have a separate allocation for every value, and it doesn't have any power fail consistency. Of course, it's not persistent at all. So if the power goes out, everything goes away, and that's what you would expect. Then there's a generic term, open addressing. An open addressing hash table, for those of you who are not experts on hash tables, is a situation in which the data records are actually stored in the hash table themselves rather than by a pointer. So it can't handle, up until now, variable length records. It could be persistent. Some of them are, some of them aren't. It could be stored on a disk or SSD. It will give you good performance because you can determine in advance where in the table approximately the record is that you're looking for if it's there, so you can get one random access. You might be able to have an incremental rehash. It depends. And the storage efficiency is great because you don't have any headers or format or anything. It's just every record has the same format in general, so you know exactly where to go and look at it, and no power fail consistency. So if you can use this one, it's great. Unfortunately, if you don't know the exact format of the record in advance, you can't, and it's not fixed, you won't be able to use it. And then there's Redis, which of course is in a different category from these others. It does handle variable length records. It is persistent optionally. I believe they have memory only ones. And I'm not an expert on Redis. This is just from reading about it and hearing about it. It can incrementally rehash the table so you don't lose performance. You don't have to wait a long time. And the storage efficiency isn't very good because, again, you have a separate allocation for every record, every value. And you can have power fail consistency. That depends. And then there's the Two Misses algorithm. It is variable length, but it's variable length in a different way than any other previously existing variable length handling hash table, and I'll describe that in the upcoming slide. Persistence is optional. There's a DRAM version, and then you can have it on a storage device. There's one or two random accesses guaranteed to any record in a file of any size. That's something that the other variable length capable hash tables cannot provide. It does have incremental rehashing. The storage efficiency is good. It's not as good as open addressing because you have to have some kind of header, sort of like a network thing where you say, well, this is the size of this, then you have a variable length. item. And power fail consistency is optional. It slows it down a lot. But if you were going to use an unordered map before, then you don't have to worry about that, obviously. And then all of these, except for Redis, are embedded and single-threaded. And Redis is server and multiple-threaded. So when would you choose this hash table over others? Well, one way you can determine this is you say, am I using unordered map or a similar node-based hash table because I need variable length capabilities? And in addition to that, any of the following are true. You want better storage efficiency and or better speed than these other algorithms. You want incremental rehashing rather than a big bang rehash, which some of the others do and some don't have. And you want the option to persist your data across program termination, so it's not just an in-memory version. But you wouldn't use it if any of the following are true. You want multi-user operation via threading, and I'll describe why that doesn't work in this case. You want a server-based system rather than embedded, or you want an open source solution. The 2misses hash table is proprietary code. So the question is, what is the possible speed that we could get in theory for a hash table based on persistent memory storage? And that's what most of this is about, persistent memory, because I wrote it before the Intel announcement. But I'll get to SSDs later. So the minimum access latency of any hash table is you need at least one random access to the underlying memory or storage, because the whole point of a hash table is to distribute the records all over the place. And so therefore, if you give a key and you want a value back, it's going to have to do a random access to the table wherever that's stored. Not assuming uniform access. Obviously, if you have extremely skewed things, then you can do better, but I'm assuming uniform. For fixed length records, the open addressing that I described before achieves this minimum because you can go to close to the place in the table where the record will be stored. But for variable length record, no such solution has existed in the past. Instead, you had to have a pointer resulting in a minimum of 2 random accesses, one to go into the table to look where the pointer is, and then you follow the pointer to the actual storage. Whereas the new 2misses heterogeneous hash table achieves this theoretically optimal limit of 1 random access to retrieve a variable length record that fits directly in the table. Now, in the original persistent memory version, that was limited to somewhere around 40 bytes of key and data, because reading a lot of data, even sequentially in the file, turns out to be slower than doing 2 random accesses. This is not true for SSDs, as I'll describe later. And if you have something that is bigger than the short length, whatever that is, then you need 2 random accesses, exactly 2. One to go into the table. You may have to do a sequential search, but nothing random, and then it will point to where the data is stored in the overflow file. So how it works, because that's obviously people want to know that. Instead of dividing the table into fixed size record locations, as is done with an open addressing table, it's divided into tranches of a fixed size that is larger than any direct record that will be stored in the table itself. Longer records will use indirection, and because it's heterogeneous, you can have a mix of direct records, indirect records to short areas, indirect records to long areas, specialized records just for the user at the user's discretion, and so forth. When calculating a record location, the hashing algorithm must generate the address of the start of one of these fixed length tranches. And once the tranche address has been determined, the contents of that tranche are parsed. The beginning of a tranche containing 2 direct records may look like this. And of course, this is schematic. There's not necessarily 1 byte of record type, 1 byte of key length, 1 byte of value length, but it's the general idea, and they are variable format records. And then these records are packed within the tranche, so that in order to find the actual record you're looking for, you may have to search through a tranche or more than 1 tranche to find that particular one, but they'll all be sequential. You won't have to jump around in the table anywhere else. To store a record, first, the record size is compared to the direct record length limit I mentioned before. If it's within that limit, the record will be stored in the table itself. Otherwise, the record data is stored in an overflow file, and an indirect record pointing to that storage is created, and that's what's stored in the table. Then the size of the record to be stored in the table, which we now know whether it's the direct or pointer type, is compared to the remaining empty space in the tranche. If there's enough space to add the record, it'll be added possibly at the end of the tranche, but that's an implementation detail that may vary. Otherwise, sequential collision resolution is employed to locate a tranche containing enough free space to store the record. No further random accesses within the table will be required. It's going to be consecutive. Now, I should say something, which is that the collision resolution method is a variation of the Robin Hood hashing technique, so that a record that is farther from where it's supposed to be, where it would like to be, gets priority when you have to figure out which record, whether you have to move farther in the table or you want to swap tranches. And that makes the variance in the record retrieval time low. It keeps it down to the minimum theoretical limit. Now, of course, in any hash table, you can fill it up. If you fill it up, you're going to have to rehash. In this case, when you're storing a record, the algorithm has markers determining whether the file is nearly at its capacity. It's a heuristic model. It's not absolutely the case. There might be one little segment of the file, a big block consisting of a number of tranches, that happens to get a lot more records than the other ones, and that will start a rehashing round too early. And I'll explain why I don't keep global detailed information about this, or I can't have it in every block because that causes problems with the implementation. Each round of rehashing relocates records to different locations in the table, and the table grows in the process. This is generally done in an incremental way so as not to cause a prolonged service outage. The overflow file is not reorganized in this operation because it's just pointers to that, and that those don't have to move around. Sometimes, by the way, you can get to a point where the algorithm detects that if you keep storing records, you might run off the end of one of these big blocks. And if that happens, it will say, okay, we have to finish the rehashing. If it was started, we have to take the thing offline so we don't end up with an overflow and losing data. Now, to look up a record, you generate the same calculation of the target tranche. You search it, the initial one, it's searched to determine whether the record is present. If so, it returns a reference to the record data. This is a memory mapped file algorithm, memory mapped persistent memory, and if it's persistent memory. So it doesn't make a copy, and typically, as used for best performance, it doesn't make a copy of data. It gives you back the address, the memory mapped address of where the record value is stored. So you can do something with it, you can calculate with it, you can do statistics on it, whatever, without actually having to make a copy of it. And there's reasons why that's superior, there's a number of reasons why that's superior, which I'll get to later. Otherwise, if the target tranche doesn't have the record, then an algorithm compatible with the collision resolution method used for storing a record is used to determine whether it might be in another tranche. And it can tell that because with Robin Hood hashing, if you're farther from where you were looking, then if you're farther away than a certain level from a number of tranches from where you started, you can tell that it can't be in the file. So you don't have to go to the end of the file. It's one of the advantages of Robin Hood hashing in general. So you can determine that it's not going to be there. And all these tranches are organized into bigger blocks, and no record can ever go past the end of a bigger block. So you know it is a localized area. Question? No question. If so, it could be in another tranche in that same big block. Then the search continues, otherwise it returns not found. And as I said before, since this algorithm makes exactly one random access to the table itself, which locates the initial tranche, and one optional additional random access to access data in the overflow file if it's an indirect record, the maximum number of random accesses to retrieve any record by key is 2. So I can guarantee it'll never be more than 2. And as we'll see later, with SSDs, that limit is big enough, the size limit is big enough that in many cases you only have one maximum cache miss, which is what that is. Okay, now, this sounds great. It's not so easy as you might guess. There's roughly 8,000 engineering hours in the current version of this. So it's not, you know, there were a lot of things that I had to discover and then a lot of things I had to work around. So here's a little quiz. I'm going to give you a bunch of statements and you'll tell me, I'll just put them all. I guess I can read them. Doesn't matter which CPU socket your program runs on. Is this true or false? You lose 90% of your performance roughly with a window with a Hyper-V VM. Retrieval speeds are reduced after the file is rehashed. Reading during rehashing, that's not why you're actually relocating records, but you relocate some records and you do some other operation, relocate some more records. And if you have an integer key, which is not that unusual, there will be no significant performance penalty for using a bitmap to keep track of the existence of billions of records. Billions of bits, that's not much data, right? Okay, anybody want to guess how many of these or which ones of these are true? Okay. None of them are true, or none of them is true. If you're running on the wrong socket, that is, you have a DIMM, and then the socket is over here, then you can end up with a round trip over the ultra-path interconnect, and it can cost you 200 nanoseconds, which is a lot in this case. Hyper-Vs don't have a lot of, Hyper-V VMs don't have a lot of performance penalties. There's one performance penalty that I've seen sometimes that I'll describe later. I'm not sure exactly what causes it, but I think it has to do with the fact that you can't, as far as I know, you can't say, take all the assign virtual CPUs to real cores on this socket. There may be a way to do it. If there is, I wasn't able to find it. So it might end up being, I'm saying it might be on the wrong, that's the same thing as the other one, obviously, the first one. Retrieval latency is not necessarily increased after rehashing, typically is not unless you rehash a lot of times because the random number generator can take a while if you do it, but again, you have to do it a lot because it's pretty fast. Reading while rehashing in between individual pieces, blocks being rehashed can be as fast as when not rehashing. And using a bitmap to keep track of the existence of billions of records can reduce performance by about 15%. And that's because it pollutes the page cache. And when you're doing all the TLB misses that you have with a gigantic hash table, this pushes some of those. I think that's what causes it. I've done some testing and it's pretty expensive. Okay, so you have, those are all examples of those are all specific examples, but there's general rules to live by besides some of the hardware dependent issues, specific hardware dependent. Do not employ large auxiliary data structures that are bigger than the cache size. In fact, don't even do it if they're smaller than the cache size if you have choice. A few hundred bytes, a few kilobytes, okay. Megabytes, dozens, hundreds of megabytes, you will regret it because you're going to, as I said, you're going to pollute the page cache, the TLB misses are going to be more, and that's a large part of the total time it takes to retrieve a record. So do not make system calls in the hot path. System call can take microseconds. We're talking about less than a microsecond for a retrieval. That's not going to work. Avoid dynamic memory allocation in the hot path. That even is sufficiently slow to cause you problems. So that's why you return the actual memory mapped record data rather than making a copy of it, because then you have an allocation and a free if you make a copy. And avoid unnecessary object creation even on the stack in the hot path. This was an interesting one. I discovered there was an auxiliary structure that I didn't absolutely have to have, but it was easier if I did it that way. And just clearing that auxiliary structure millions of times was noticeable in the performance results. And minimize UPI traffic to the extent possible. I already discussed that. Now, what implications in terms of, those are nice rules, but what does that mean to the implementation? Since large auxiliary data structures can cause excessive page table lookups, you need a directory list structure for the hash table. Because you have a directory, you go to the directory index and you do something there, and then that tells you where the record is. Not good. You don't want to do that. And then you can't use normal multi-threading techniques like standard thread because that will take longer. I tried it. Every time I tried to do that, the program ended up being slower running on multiple core, multiple threads than it was single thread. So that's not going to work. Okay. Now, how does that affect the API? Well, for ease of use, there is the simple interface that looks like an unordered map, as I described earlier. So it's an index, the index operator, and it gives you back the value, or you store it, and it's very nice and easy to use, but it makes a copy. It does a memory allocation and a free and a copy, so that's not great. But if you want maximum performance, and that one will give you a standard string, which causes a heap memory allocation and deallocation, and if you want to modify the value, it has to do the lookup again. So that's because it doesn't cache those. So that's going to add some more time if you're going to make a change. The advanced interface doesn't make a copy, but returns a C++ object similar to a string view, but it's older than that. This library is a derivative of one that's really, really old, and string view didn't exist at the time. Also, this one has, in addition to the address and the length, it has a maximum length, so you can change the logical length of the object of the thing being pointed to without actually making a copy or changing anything. I'm not using that typically in this interface, but it was there, so I used it. So you don't have to have any heap memory allocations or deallocations in this case. And you can also update in place. So it gives you back, you have an update function, and it gives you the string view-like thing, and you say, okay, starting at this offset into that, write these, n bytes onto that. And it will tell you if you try to go off the end, you'll get an error. Other API considerations. The algorithm can move records around at any time there is an add or a delete operation, because of the Robinhood hashing. Just adding a record may cause other records to be relocated. So for this reason, you can't keep validly an existing reference to a record after adding a new record, deleting a record, or replacing a record with a value of a different length. Updating in place doesn't move it. Replacing it with a value, replacing a value with a new value of the same length does not invalidate it, because it writes on top again, just as the update does. It has a special case for that. And iterators, for the same reason, must be considered invalid after those same operations. For the same reason, the things can move around. So, okay, that sounds like a lot of work. What do we get for doing this, or what can we get for doing this? So here's my old server, which has Xeon Silver 4215, two of those. It's got Optane Series 100, the original version, 128 gigabytes of RAM, but that doesn't really matter in this case because it doesn't use much RAM. Okay, I can retrieve 1 million records a second of 8-byte value, 8-byte key average. Again, these are variable. The 95th percentile retrieval or update latency, 1.6 microseconds. With medium records, which actually have a pointer, there's actually a pointer to where the data is stored, you can get over 600,000 a second, and it's 2.4 microsecond 95th percentile latency. It's almost flat latency, and the number of records almost doesn't make any difference. You can add new records somewhat faster than retrieving, because it adds at the end of each tranche, unless you have to do the swapping, which usually, most of the time, you don't have to do. And these records were gathered at these results were gathered at a 1 billion record file size. So it's like a 200 gigabyte file, something like that. And it's flat. I've tested it through tens of billions of records, and the performance is flat. And as I described this, the dual Xeon 2nd generation Silver 4215 on Windows. Ubuntu is a little bit faster, and the reason I think is because, well, I know the reason is because, one of the reasons is that the mapping is in bigger chunks. You have the huge pages, so the TLB reload isn't as expensive as what it amounts to, so you save there. Now, in the latest generation hardware, this is Xeon 3rd generation, Gold 6326. I have it down below. It's about the same speed for the short records. It just doesn't make that much difference because it's limited by the persistent memory, and the persistent memory was supposed to be a lot faster in the Series 200, and it depends, but I haven't noticed a tremendous difference. In 1.6 microseconds, the latency is about the same as before. You can get an extra 100,000, it's like 15% better with medium records, and but the retrieval and update latency I don't think is any better. If it is, it's only a tiny bit. Adding new records 50% faster while you're not rehashing, and again 1 billion record file size and flat through tens of billions. And here's what this machine is. I don't have a Linux install in this. I cannot imagine that it would make that much difference compared to the older server. It has to be about the same, and Windows 10. Now, if you have enough memory that the hash table gets loaded into memory, that's a lot faster. I mean, obviously that's not with persistent memory, but if this data is on an SSD and then you run the thing for a while till everything is loaded in memory, you get a lot higher performance. Then you get 1.6 million records a second, the short records, with a 0.8 microsecond average latency, sorry, 95th percentile. About 1 million medium records and 1.5 microseconds, because again, it's a faster medium. Adding new records isn't much faster than retrieving in this circumstance because the read-write performance for DRAM is almost the same, whereas with Optane, it's a lot slower, obviously. So if you're just adding stuff at the end, does that make any sense? No, never mind. Never mind I said that. I don't know why. I don't know why there's not much difference. And this short record speeds are tested at 4 billion records because that's all the memory I had, and medium records at 500 million records count, both limited by DRAM. And that's the older server, as I said. Now, for the latest generation hardware, you get another 15% performance, and you're down to 3/4 of a microsecond retrieval, the 95th percentile. About 1 million medium records, that's about the same. And the latency is that 95th percentile is a little bit faster, but not much. Again, adding records is a little bit faster than retrieving. And this is limited, this is at 9 billion records, short records, and 1 billion medium records, again, limited by DRAM. I have 256 gigabytes, and that's the 256 gigabytes. So how fast could you possibly run if you had no other overhead? So here's theory versus practice. So with 50% read, 50% update on persistent memory with the previous generation server, it says the Visual Studio Profiler, which is pretty good in this circumstance, it says almost all of the time, or 50% of the time, is spent on one instruction, one line of code, which is the store operation or read operation. So about 50% of the time is spent reading and writing. We're getting an average total latency of about a microsecond, 1,000 nanoseconds, and a persistent memory random access is about 350 nanoseconds because we're reading randomly. And the write doesn't add that much, which is interesting. It's not much slower because I guess it has it cached. I don't know what the reason is. You have to ask the Intel people. So no one could ever go more than 3 times this speed, no matter what algorithm they had or anything else about the program, because you're limited by that. And I don't think you can get very close to that, but that's just an opinion. Now with medium records, with 10-byte keys and 100-byte values, about 70% of the time is spent reading and writing. So with 1,500 nanosecond total latency, even if you had an algorithm that required only one persistent random access, memory random access, you would have to take 350 nanoseconds. And I don't think that's actually possible, but somebody could, of course, prove me wrong because nobody thought you could do variable length records directly in a hash table, and that turned out not to be true. So you can't go more than 4 times the speed. And as we see in the SSD case, I can get closer to the maximum possible performance. So is it applicable to DRAM or SSD? Yes, the DRAM results are basically the same as the DRAM cached memory mapped hash table where it's on SSD and it's all loaded in. Although, of course, the startup and shutdown, having to wait for it to get loaded in, to get cached in, is not going to happen. Of course, you won't get any persistence in that case. And in fact, the way the program is written currently, if you create the table and you let the object expire, it throws everything away. So you can do it in a row though. You can say create table, make modifications, blah, 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 calculate statistics. That you can do the way it is right now with the DRAM version, but obviously you're not going to have persistence if it shuts down and the thing goes away. Now with SSD is very interesting, and this is what I started working on as soon as I heard the Intel news. I said, okay, well, how am I going to keep anybody's interest in this when that's going away? One would expect that the SSD performance will not be the same order of magnitude as with DRAM or persistent memory, because the fastest SSD theoretically is 5 to 10 microseconds, but I haven't actually seen a sustained. That's Optane SSD, which again is going away. It's more like 100 microseconds generally for a pretty fast SSD like the Samsungs or DAPUSTOR. However, one thing you can do, as I said before, multi-threading of a normal type won't work because there's too much overhead, but you can shard the hash table, and that's what I have done. So I have a multi-processing version that splits it into multiple shards that don't have to coordinate very closely, that it uses a batch method. Somebody talked about that in one of the discussions earlier. So you can batch a bunch of records for each shard, and then they work on them independently, then you synchronize once in a while. So how much throughput can we get with an SSD? Now, this here is for the 8-byte key and value, again, variable length, 100% read, and I used very big tranches, and I'll explain why that is. On the old server, I could only do 16 shards because I only have 32 hyper threads, so I couldn't just use them all up for this. It wouldn't work very well. If you read the records, start from the bottom of the table. If you read the records in a different order than you wrote them, you can get on the Optane SSD about 129,000 records a second with this multi-processing version. But if you read 1 billion records in the same order you wrote them after a few minutes to warm up so that all the page tables are all up to date and so forth, you can get 1.7 million records a second. Now, this is a hash table on an SSD, and it's not because of memory caching. So, after 8, and it will slow down, and I know part of the reason why that happens. I'm not sure of all the reasons. I haven't had time to do all the experiments to figure that out, but the overall throughput is still 1.2 million records a second with the Optane SSD. However, that's a Gen 3 device. The Gen 4 Samsung or DAPUSTOR, as you'll see, is almost the same. With 32 shards on the new server, we're getting 6.1 million records a second if you read them back in the same order that they were written in. Now, this was very surprising to me originally because I said, well, it's a hash table. You're storing things in random order, right? You're storing things in random order. How can it matter what order you read them back in, even if it's the same order or a different order? Anybody want to guess what was actually going on there? Some people know, I know, but what's that? Nope, it's not caching. This file is 3 times the size of memory, and it doesn't matter how big it is. It was something I had no idea what it was actually. And it turns out it's because of the flash translation layer. What happens is I'm writing block 1,000,000, then I'm writing block 1,000, then I'm writing block 47,000, then I'm writing block 2,000,000. And you know what the SSD says? Oh, okay, that's block 0, 1, 2, and 3. If it's clear, if those blocks are all available, it will do it in that order. So when I read it back in the same order, logically, it's all over the file. Physically, it's in a row. And what this means, of course, is, as I said, you get tremendous performance, which slows down after a half an hour. You're still at 3.3 million records a second on with the Samsung. But what's interesting about this, you say, okay, well, that's cool, but couldn't you do this with another kind of hash table? And the answer is no, because variable length records require at least 2 places to store them, and it's not going to be a streaming read of a big block like this is. So the records must be embedded in the table itself to get this, again, I haven't proven this, I didn't have time to do this, but logically, the other allocations of the little record, the 100 byte or 1,000 byte records are going to be, sprinkled around. However the SSD allocates those, it's not going to be like this. They're not going to be all in a row the way you would like them to be. So the numbers here are, as I said, you have a Samsung 980 Pro, it's Gen 4, and the reason why Gen 4 matters a lot is because it's basically sequential. These original order reads are basically sequential reads. Notice that the different order numbers are not only not very good, but they're not that much different between the different storage technologies. It's just the sequential reads. Now here's read and update. The first one was 100% read. Read and update. I do not recommend running this for a long time with the Samsung SSD, or you're going to need a new SSD because it doesn't have the endurance. The DAPUStore, they say you can do 100 drive writes a day, so I'm not too worried about that. Now here we're getting 1300 for the Optane in a row, 1300 versus 1700K, and 1000 versus 1300, whatever it was before. There was something wrong with the overall throughput in different order in the Optane test. I don't know what happened. It started going real fast after the end of after about 1500 seconds. Maybe it hit a patch where they were all in the same order. I don't know what it was. So I just filtered that out. I said, I'm going to take up to where it's acting normally like everything else does. That was 108,000. 95,000 for the Samsung. The DAPUStore did better because its write performance is better. That's just what they like. But even with this, even with read and update, you're getting 5,600K, 5.7 million records a second, 2 3/4 millions a second for 1,800 seconds. And the DAPUStore is somewhat slower. So comments on the SSD performance results I already mentioned. It's faster or the same speed as the DAPUStore, but you'll burn it out if you use it with write-heavy loads. The large tranches provide much better performance on SSD, even for short records, because you're getting these big blocks that you're reading sequentially rather than doing everything randomly. And with the Optane persistent memory or DRAM, the small tranches are faster because sequential reads there are only twice as fast or something as random reads, and SSD are like 100 times as fast. So you really want it to be as sequential as possible with the slower devices. And this is the key thing as far as SSDs. Records up to the tranche size limit, which as I said is 32,000 approximately, in the SSD built version of the program. It's a compile time constant. Can be retrieved with exactly one random access. You will never have to do more than one random access to get a record from anywhere in a file of any size up to that 32,000 byte limit. So you would think that would be of some interest to SSD manufacturer or hard drive computational storage manufacturers, given that one random access is the best you could ever do. I mean, you can't do better than that if the data is reasonably uniform. And as I said, the most unexpected result was that the performance was so much better with reading them back in the same order. But now I know, and I originally said I didn't know why that was, but then somebody, I forget what his name was, from Microsoft, when I told him about this on Monday, he said, "Oh yeah, that's because they're not written in the logical order. The physical order is the way you wrote is the order in which you wrote them, not the order where you think they are in the file." So that's the flash translation layer will give them to you in physical sequential order. Now, once in a while, when you're doing stores, if you haven't done a full erase of the SSD, you will get a garbage collection pause. But I mean, that's, if you don't want that, then make sure it's erased before you write. That's not the algorithm's problem, I guess. And then what about computational storage? Well, I think it's very applicable to that because no directory, no big DRAM allocation, no index, and no extra accesses. So if you want to be able to know, given a key that you want to be able to get to it in one random access, then you don't have to have, I mean, this thing I think uses, well, if you're not generating keys and storing them and permuting them, basically the program itself, retrieval, takes a few megabytes of memory. The actual the executable is like, it's less than a megabyte. So with all the all my test code and everything in it, the library itself is a few hundred kilobytes. I haven't measured recently, but it's not very big. So you could put that on a computational storage controller and not use up a lot of resources and get the maximum possible theoretical performance for a hash table that's built into a KV SSD or a hash SSD, because it's not ordered. And the fact that you can read records back in the same order, I don't know what the use case is. I think there has to be a use case where you know in advance that you're often going to want to retrieve these records in a particular order. I don't know what it is. It may not be any such thing. I don't know, but at least you get the single access. You get that anyway, whether you're doing that, and that's not as fast, but it's still faster than any other way to do it. And then notes. There's a patent issued on this algorithm. An earlier version of the algorithm doesn't work exactly the same way. The basis is the same, the variable length records packed into fixed length tranches. That's all described in the patent. We have other US and foreign patents pending. And I mentioned this thing about the virtual machine overhead. As I said, somebody who knows a bit more about Hyper-V than I do might be able to say, oh yeah, that's because, there is a way to do it. You have to set some bizarre, whatever thing that they don't tell you about to get that to work. And also, I couldn't get the Ubuntu native installation on the same hardware to show that difference from the wrong socket. I don't know why. I was getting like 200 nanoseconds extra time, 180, 200 in Windows, but in Ubuntu, if the DIM was on the other socket from where the program is running, I couldn't reproduce it. Maybe I wasn't pinning it. Maybe the thread numbers or the core numbers are different. Or, that's very possible. It doesn't. What I thought was mapping to one socket really wasn't. I don't know. It doesn't seem like there's any way to not have that overhead. So it's probably a test. It's probably an experimental error. And then, of course, one more point, one random access to the table doesn't mean there's only one random access to memory during the lookup, because you've got the TLB, a big memory map. The TLB is going to be repopulated for virtually every user memory access request. You're not going to get any benefit from the caching because it's not the TLB is not designed with an option saying start at this address and go forever. They don't have that. I've asked about that, and people have said, yeah, we asked Intel about that 15 years ago, and they haven't said anything yet. So I'm not expecting that to be changed. Now, the transparent huge pages on Ubuntu helps with that. And, excuse me, there is more documentation. The user manual is on my website, and that's it. That's the presentation. So any questions? No question. Wow. Yes. In terms of maybe like denial of service or something. Or data placement. A question is, have I done any security analysis with regard to data placement? No, I have not. I have not done that. I mean, if you know the algorithm, the hashing algorithm, or you could deduce the hashing algorithm, then you could generate keys that would all hash to the same place or something like that. So you could have a denial of service attack on that basis. But you could also, the reason I don't do a random seed is for reproducibility and testing. There's no reason you can't do it. It's not, there's nothing inherent in the algorithm that would prevent you from doing it. You just wouldn't be able to run the same test and write it and then read it back with the same key. You wouldn't be able to file. The same key. It wouldn't be in the same place in the file, so it wouldn't be reproducible. Yes. No, I test with records with key sizes and with value sizes in excess of the 32-bit limit. That's in my regression tests. Yes.
So we once did a crude algorithm implementation of a digital circuit that came rather close to your theoretical limit of the underlying RAM. The question is, you have highly optimized the algorithm for CPUs, obviously, for caching with TLB are being good. Any ideas on turning this into a digital circuit or even more performance?
I would be thrilled to discuss that. Oh yeah, the question is, have I considered basically putting this in hardware, like an FPGA or something like that? I would love to talk about that. I have not done that. We don't have the resources. I'm not an FPGA programmer. You know, I wouldn't know where, I mean, I think it would be great. Well, I'll tell you one place where it would be terrific, for sure. And that is that I believe, and I was going to get to this, I forgot. I believe that one of the reasons why that multi-millions records per second slows down is because the records that you added later go long or farther into the tranches, and the processing, the parsing of the records takes some time. Unfortunately, you cannot use the vector instructions because they're only for certain fixed lengths, but with hardware assist, you could, I suspect it would be just completely flat, and it would help. The thing is, it looks to me like the most you could ever do with a single miss one, with one direct, is to double the speed, maybe, because that's based on the underlying storage. However, that's for the persistent memory. DRAM, of course, is several times as fast as persistent memory, as you could see, so there's more overhead there. That would be great. I would love to have a chance to work on that. I would be very happy to discuss that. Anybody else? I think we still have some time. Okay, I have a very, very short one-page description of this. The user manual is on the website, and I'll be happy to answer any questions that anybody has afterwards. So thank you very much.